Hello, everyone. For the next 30 minutes or so, I'm going to be sharing with you a use case around A/B testing. I'll talk a little bit about how we started, the questions, how we got to the answers, and maybe generalize a little bit how Bayes can help you change the way that you talk to your stakeholders. Hopefully, by the end of this talk, I'll be able to convince you that Bayesian statistics can actually give you the answers that you want, and also that it's not as frightening as it might seem to be at the beginning. At least I know this is the feedback I get sometimes. A few words about myself. So I have a lot of mathematical training in my background, but as a practicing data scientist, yeah, more than 15 years, embarrassed to admit. I've been mostly doing practicing frequentist methods when I was working for biotech companies or machine learning techniques. So I want to say I'm Bayes curious in the past few years, trying to kind of incorporate Bayesian statistics back into my workflow. Data scientist, well, sorry, in my honest opinion, the term has been completely, I would say, hyped or charged with meaning by now, right? When you say you're a data scientist, you can do so many different things. So I like to say I know some mathematics and statistics, and that my production engineers actually allow me to put some code into production. That's where I am today. No, I'm kidding. But of course, and currently in Shopify, I'm focused on forecasting and causality. We do some works around elasticity and optimization, and also problems that have to do with working inside platforms. And also, on a complete tangent, if you're doing NLP, we heard a really interesting talk now, for recommendations and search, then please feel free to hit me up. Also, I'm really interested in that. And you can find me in all the usual places, LinkedIn, Twitter, and GitHub. So, just a little bit about what I'm going to be talking about today. I'm going to start with the motivation, kind of what were the questions that we started with. I'm going to talk about the answers that we got and we wanted to get and we're getting now, and how we got to getting these answers, and mention some of the toolkits that we looked at and that we're using today. Two of the last points, I'm not going to touch too much on the two last points, just wanted to put them there as kind of placeholders to tease you a little bit to think more about these kind of things. One is what you do when you can't really do A/B testing, or when A/B testing is maybe not the right thing for you to do. And the other one, a huge topic coming from the world of engineering, problem forward versus solution backward. If there is time, I'll talk about it. If not, let's talk about this later in the office hours. So let's start. I'm sorry, the icons in my laptop, they look better, so this is kind of a simplified version. So meet Nadia. We love Nadia. Nadia is awesome because every time she has a question about the product, or every time she wants to test a new feature, or wants to test a new KPI and see what it does to the product or to the users, the first thing she does, of course, is to come to you, her beloved data scientist, and talk to you about all the right things, about sample sizes, and about the meaning of KPIs, and about the questions that we can ask, and about the answers we can get, and and what's going to be, what is the report going to look like, and what is the decision downstream. So all the right things, she comes to you first thing and starts talking to you about it, even before anything goes into, any code is even written, right? So we love Nadia. By the way, is anyone here named Nadia? Or, okay, if you know Nadia, any Nadia, I'm sure she's awesome Nadia. In reality, we don't have full control over all the stages of the process. Maybe you're working with some platform that has some testing already kind of hard-coded into it. Maybe you don't have exactly control over the duration, or the sample size, or the questions, but at least as a data scientist, you have this really healthy checkpoint where you can say, okay, given all that we have, given what we have, not what we want, but what we actually have, we can answer question A, question B, we cannot answer question C, and for some other questions, well, maybe we need to run the test differently. So at least you have this way of controlling the conversation, or giving some kind of checkpoints and sanity checks on what's going to happen, so it doesn't end up when you run a test and then you can't really get any answers from it, right? So this is a pretty realistic scenario. Again, some place to start, but try to do better. In some situations, well, maybe you started your job as a product data scientist, or working for the marketing department, and you come to work and Nadia comes to you with a ton of data from experiments that you didn't run, that were maybe misspecified, or the KPIs were not designed correctly, or maybe there was not even a test, or maybe there was no testing done like in a proper way, and you kind of need to start figuring out what can you even do about this. Bayes can actually help you there. I'll just mention it briefly at the end and maybe send you some examples that, and some code that might be interesting for you. But let's talk about reasonable, Nadia. And when you have a question, when you want to test a new feature, for example, or test something else about the product or a marketing campaign or whatever, hopefully you have all of these set up in a satisfactory way, and this would be having a good understanding of causality, right? We want to change the feature, and we expect whatever, user happiness to increase, or we expect revenues to increase, or something to be better, right? There's a KPI at the end that needs to be impacted, and we want to understand at least the causality of what impacts what. It's an important thing to have. We also have KPIs. Well, we heard some talks about today and yesterday. KPI sounds sometimes really, really easy, right? We just count things. Well, counting things can be really, really hard. You need to go to the other room to hear how hard it can be sometimes when you talk to the data engineers. But let's say we do have some understanding of that. The last three are sometimes harder than you think. Even, you might think you are in a good place. Sometimes you need to think about it a little bit harder. So volume versus velocity, the classic trade-off. I want to ask a question about a really small segment of users or some feature that's rarely being used. I only get a few clicks every month. So if I need to wait 6 months in order to accumulate enough data and enough exposure of the control and the test to answer the question, maybe in 6 months this is no longer a relevant question, right? So we need to think about velocity when we design these kind of things. And also, again, about volume, because we can get non-significant results that won't be very interesting if we don't have enough users. So it is something to think about. There's also the flip side where things change too quickly, meaning that, if you think about examples like ads, so clicking on ads or showing ads to users, sometimes you live in a really dynamic environment, and taking 3 months or even 2 weeks to get to a decision is too slow. By the time you kind of collect the data, build your model, or run the test, update your assumptions, 2 weeks have passed and things have changed completely. You need something faster. So it is something at least to consider, is A/B testing even relevant here? I'll get to that at the end. The last point, when I was writing these slides, I was thinking about the situation I've encountered before, where you start working for a very small company, they maybe already wrote some kind of a backend. They didn't really think at the beginning about integrating with any kind of testing platform or testing services. So running a test is actually just technically difficult. That can happen sometimes. Maybe you are in a better place than I was in some parts of my career, where you already integrated, the platforms today are much better than they used to be, and they integrate very easily with these testing services. So that's actually not as hard as it used to be. I actually discovered a few months ago that I think Apple just joined Google and Mozilla. Google just joined Apple and Mozilla with blocking cross-domain tracking. So basically, it's going to be harder to track users across different domains. Those of you who have been working in the marketing space should be really, really aware of this, because if you don't have good tracking of users along the entire journey, and you only see parts of it, when users move between domains or in different parts of the funnel, you are going to get really, really skewed results. So you need to be really aware of getting the full picture and getting it correctly. But let's say, with all of these caveats, we are in a place that we're happy with, and we think we can move forward with the A/B testing. So what does Nadia want to know? Nadia wants to know if the new feature is working. That's a basic question. That's what we're here for, right? We want to know if the new feature is better than the old one. We just heard a talk. Is the new chatbot better than the old one? Or whatever. Is the ad campaign better than not doing anything or something, or whatever? Just a little pet peeve of mine, you run a test, you look at the data, people start talking about significance or p-values or whatever. Just look at the data first. Sometimes you pass I love this acronym, the intraocular trauma test, meaning that it just hits you between the eyes, right? So if you're there, you're lucky. But I really encourage you just, first thing, just look at the data. Sometimes you can just see things there. I remember working for a biotech company, working with some researchers, doctors, medical doctors, and we had a lot of discussions, again, because we wanted to publish the results in a good journal. And the doctors told us at some point, we can wait with the p-values and the sample size and everything. If I can't see the results with my eyes, if I need statistics to prove that something's working, we're already in trouble, right? But life is noisy and complicated, and sometimes you want to measure something, a really small effect, in a really noisy environment, and this is why, we run the test. And we run the test, we collect the data, and then we go and meet Nadia, to conclude the whole thing. And Nadia wants to know, okay, Is it working? Is the new feature better? Is the campaign working? Whatever. And here starts this little strange song and dance that we as data scientists often do, because let's be honest, we can't really answer that question directly when we do A/B testing. What we can say is the following. We saw an increase of 5% in this KPI or in this conversion rate or whatever with a p-value of 0.05%. Okay. This is great, right? This is really interesting, but this is not the answer to Nadia's question. The problem is, Nadia thinks that you answered the question. When people hear this is statistically significant, people think, okay, this is working. And this is absolutely not the case. So, I promise the only math equations you're going to see today, promise. What is p-value? So I can read this to you. P-value, okay, it's a probability of seeing the data conditional on the null hypothesis that it's not working. What does it mean in a human language? It means, imagine a parallel universe, a galaxy far, far away, where there is no effect, where the new feature is not working. This is not a hypothesis, this is not an idea. This is the absolute concise reality of things. We're talking philosophy here, you understand? This is the absolute reality of things. And in this parallel universe, we run an experiment. There is no effect, we shouldn't see anything. And we see the data that we see, and we are surprised. That is p-value. That is what p-value quantifies. P-value quantifies surprise in a universe when there is no effect, when there's no change. And this is not the same as answering the question, is it working? It's not the same thing. This is what Nadia actually wants to know. Nadia wants to know, it's called the posterior distribution, or again, probability that something is working, or where is the KPI, where we think the KPI is now having seen the data. It's called the posterior distribution. This is actually the answer Nadia wants, or Nadia needs. And in order to calculate this quantity, we need to calculate three different things. One is the likelihood, which comes from the model. In the case of A/B testing, it's a very, very simple thing. The second thing, the probability of the data, which is something a little bit harder to calculate. Luckily, the tools that we have today are much better at it. One of the reasons Bayesian statistics kind of lag behind machine learning and frequentist approaches is because this historically was really hard to calculate. It's not the case now. It's getting much better. And the third one is the prior. We'll get to the prior. Before that, I just wanted to mention, so what led me to think about Bayesian statistics? Because first of all, I just wanted to answer the damn question. I wanted to be able to answer the question, is something working, yes or no? Or at least what's the probability that it's working? Again, p-values, I started realizing there are actually, well, not just me, there are a source of miscommunication. There is a really cool article that someone wrote with really nice examples on huge effects with really high p-values, no effects with really low p-values. You can get all of this real weird mixture together in all these examples. And there is a name, if you want a title, it's called the replication crisis that hit social science and biology pretty hard. I started reading papers about people from growth teams in companies that kind of, these teams that come in and try to do a lot of testing and optimization of products or funnels. And they are complaining now that, okay, I ran a lot of tests, I chose the feature I thought were best, and when I put it in productions, I don't see the results I expected. So I think it just creates a lot of miscommunication. Bayesian statistics is also a good way of thinking about problems. I'll touch that briefly. And you also have really good tools that I think put in place really good processes. So I mentioned the three quantities. I promised I'll talk about the prior, because prior is maybe the most tricky, maybe the most controversial part of this process. Quoting from Wikipedia, and this is my comment in the middle, the prior distribution, the probability distribution that would express one's beliefs, that's my comment, yes, this is a belief, about the quantity before some evidence is taken into account. So imagine the situation, you have your models, let's say really good model, conversion model for the US, and you want to run an experiment or want to test something in France, and you have no information. A prior distribution is me coming to you before seeing any information from, let's say, France or Spain, and asking you, where do you think the conversion rate is? So this is where, and we heard talks yesterday about expert opinion, about integrating subject matter expert into your team in a good way. This is where Bayesian statistics kind of forces you to do it, in a way. The process is built in, because you have to go and ask people, what do you think is going on before seeing anything? It's part of the process that you have to do. But luckily, again, distributions are a flexible thing. And if, for example, I think it's probably around 50%, but I'm not sure, then look at the orange line, right? centered at 50%, but gives a lot of probability mass to other values as well. Maybe I think it's either 0 or 1, but probably not in the middle. Then look at the red line. Most of the probability sits at either 0 or 1. It's called a horseshoe prior also. And I don't think there's anything happening, not in the middle, like people either go here or there. Maybe it's another thing. Maybe I think it's, my expert told me, we think it's around 20%, but we're not sure, so maybe I'll use the purple line over there to quantify my belief before doing anything. So we need to do that. And again, choosing a prior, I said this is subjective, but there are really good guidelines. Sometimes you have these natural constraints. Some KPIs are only positive, so you need to choose a positive distribution. Sometimes, A/B testing, if you want to be really conservative, then you can say, okay, the distribution is centered around 0, and you just need to kind of decide how uncertain you are. You can do a lot of really cool exercises that engage your stakeholders in a really meaningful conversation about what we expect to see, where we think the effect would be, versus where we see it after we look at the data and run the experiment. Again, really, really healthy discussions to have with stakeholders around where we think we are, when we think we're going, and also explains to you as a data scientist what people think, what are the expectations. You can discover really interesting things sometimes. And also for the stakeholders to kind of get a better picture of what you're doing. And you can do cool things like gamification and other things, that you usually do with training sets. If you're lucky, you have some benchmarks sometimes. And sometimes your tool just restricts you some very simple choices, and then you just need to be smart about making these simple choices. Sometimes you can just choose some Gaussian form, and then you just need to choose which one to go that kind of makes sense. Beyond that, you can go pretty crazy with Bayesian models. You can build really complicated ones, and then choosing priors becomes really difficult. Think about just what is a prior over a correlation matrix of some different phenomena that you're looking at. That becomes really tricky, but there are really good guidelines. There's a link to a paper by Michael Betancourt, one of the main contributors to STAN, that wrote a really, really good paper about this, recommended reading. But think about it this way: you just got a new job description. You translate business insights into distributions, and this is a new role for you as a data scientist. So let's say we got some opinions, some prior opinions about where we think the effect should be. Again, A/B testing is pretty simple. It's 0, but we can quantify how uncertain we are what the effect is going to be. And we collect the data, we calculate the posterior distribution, and then we go again to sit down with Nadia, and she asks again, okay, I listened to you talk for hours about Bayesian statistics, and you convinced me that this is good. We let you build your models and everything. Can you please tell me if the new feature is working? And the answer is yes. So if you look at the posterior distribution there, we looked at the data, and given everything that we kind of know and everything that we collected, we now think that if I had to give a number, like a single number, I would probably say that effectively is what I'm measuring is around 2, right? This is kind of the peak of the distribution when you have these nice little peaks. But we can do much more, because we can start talking about certainty and uncertainty. We can start saying, okay, 95% probability that this is between 0 and 5. It's called high density interval. There's also EDI. I forgot what the E stands for, but it means that you kind of chop 2 equal tails from both sides. Sometimes they're the same, sometimes not. So we can say, okay, this is where we think it is, and this is where we are 95% certain that it is. This is not the same as confidence interval. That's not what confidence interval stands for. Please, again, if this is not clear, I hope it's clear now. Confidence interval, again, talks about this alternate reality. And here we say, in this reality, we think, having seen the data, that this is where the KPI is now living. But we can answer more questions. For example, we talked about, again, running a test, seeing positive results, putting something in production. Maybe we're not really certain about these positive results. What is the risk we're taking here, right? What's the probability we're actually going to do damage? We can answer that. Because we can look at the probability of being below 0, okay, of the difference being actually negative, and say, look, everything looks great. There is a 20% chance we're actually doing damage. Are you willing to take that chance? Again, a different conversation to have with your stakeholders as data scientists. Not just what we see, but also talking about risks as well. Same, it's called type S, type sign error. Same thing for magnitude. We see 2. What's the probability that it's 20 or 200 or kind of completely off the scale? We can say how sure we are about that. A really, really good thing that happened, especially when you talk about features, sometimes there's some kind of a budget involved in the conversation that you need to take into account. So sometimes Nadia will tell you anything below 3% does not justify the changes we need to do in production in order to deploy this. What is the risk we're taking here in terms of not returning the investment? So it's not just zero, it's basically any threshold that you want to set. You can say, what's the probability being above or below the threshold? And then your stakeholders can take really data-driven decisions, right? This is a really, really cool feature here. I'm not going to go into Bayes factors. There is some argument about them because they kind of try to go around the prior, but maybe for a different talk. So hopefully I've convinced you that this is a really great set of answers and really great set of questions to ask and answers to get. How do we get them? Well, there are a lot of tools out there. Again, trying to put it on a graph. There are what I call the low-level frameworks. I think perhaps my favorite and maybe one of the most prominent in the past years is Stan. It's not written, it's kind of language agnostic. It has bindings to Python and to R and to other languages as well. You need to learn a new language in a sense and a new way of working with a new programming language and some new tools and new ideas. But it's portable, it's cross-platform, and it's super powerful and super flexible. You can really start with a clean slate. You don't have to have any assumption. You can start with a clean slate and kind of build your model, a really complicated model. Again, A/B testing may be a little bit of an overkill. You can use some nicer packages, but if you want to go further, I highly recommend that you at least look into those, into Stan. PyMC3 is a pure Python package, and there are other ones, I guess older ones, bugs and jugs and all these kind of things that have usually bindings to R and Python and other languages. Somewhere in the middle, there are these frameworks. I like BSTS, I've used it a lot. For other use cases where you can do A/B testing, it's frameworks that are actually really flexible and really powerful, but usually designed to solve a specific problem. BSTS is designed to solve time series issues and causality, but they give you a lot of flexibility, but there is a trade-off there. You can only choose some distribution, some structures, they have some assumptions behind them, and kind of last but definitely not least are all the nice free candy that you can get thanks to the wonderful open source community. People write, a lot of wrappers around these frameworks. One of the famous one, Prophet, which made a lot of noise from Facebook, it's a wrapper around Stan that does time series forecasting. It's focused around trends, not around, more around trends, less around causality. So great to use as long as you understand what you're wrapping around, right? That you understand the model. BRMS, Stan ARM, maybe more useful if you go for A/B testing. You can actually run the A/B, you can actually calculate things in those packages, and they give you the nice R syntax that you use from linear regression. BSTS is actually what's powering Google's causal impact, for those of you who've heard about it. So that's what's powering that. Again, it's a wrapper around it. Really nice, like one-liner that can do really complicated things. And there's a whole universe of R packages. I just wanted to mention two, BEST and BaseSR, which are kind of really simple, focused on A/B testing and these kind of simple questions, and can sometimes help you guide you through the process if you're new to this. Just a few mentions of things beyond A/B testing. I promise I'll just say a few words about this. A/B testing is wonderful. It's the best way to answer questions, except when it's not. So when isn't it? When isn't it a good way to answer questions? When you're outside this, what's called in physics the Goldilocks zone, not too hot, not too cold, not too bright, not too dark. There's a really narrow band where life can exist. So too fast, too slow. So where things are too slow, again, when it takes 6 months to gather enough information to answer a question, maybe A/B testing is not the right thing to do. And again, with Bayesian statistics, you can inject more information through the priors, kind of say, I'm pretty sure this is what's happening, and let slow trickle of data kind of update your beliefs as you go. So at least you can start from somewhere. So it helps that. Also, you can run a lot of A/B tests a long time, like these disjointed tests, and completely miss the fact that there is an underlying phenomenon because it's just happening really slowly. There's a change in the market, new competition you haven't heard of, just changing your customer base or whatever, something's changing underground. And when you're able to combine these tests into a single test, into a single model, you can actually inject the effect of time into your model throughout the different A/B tests. This is kind of this idea of pooling or hierarchical models. There's one time trend in the background that kind of affects your test a long time. And you can actually incorporate that into your models and catch this, okay? Where you if you just run a disjointed set of A/B tests, you can stay pretty blind. Same thing for too fast. Sometimes you need to make a really fast decision, so which ad to show to which customer. If you need to update your model every week or every 2 weeks, maybe that's too slow. There's a whole universe of tools around that with the Bayesian. For those who heard of multi-arm bandits, that's, I think, kind of the almost industry standard today. It's a Bayesian method that basically helps you make decisions really, really fast when you don't want to do the cycle of, collect data, stop, update the model, stop, deploy a new decision model, stop, collect new data, stop. You need to do things in real time. And the same thing I mentioned before, this pooling idea. If you only have a really small segment that you're interested in, you don't have enough information kind of to make a lot of inference around them, but you do want to try and see something. Are they different? How different are they? Bayesian tools are really, really great for that because you can do something called pooling. Insurance companies, for example, I worked a lot with in the insurance space. So, you have your portfolio and you want to calculate the risk in order to calculate your premium, right? How risky you are as a customer. And sometimes you only have one Maserati in your portfolio. So how do you calculate the risk for, n equals 1? There are actually interesting ways of doing that. And again, I encourage you to investigate that. Other cases where, okay, you just can't test. It's just not possible. Technically, legally, from a regulatory perspective, and what do you do then? How do you say something is working, especially when there's a lot of noise? Again, really, really cool concepts from Bayesian Statistics. This is an example I presented in London 2 weeks ago with causal impact from Google and how we kind of try to see, okay, we had to release a public campaign. How can you prove that the campaign had any effect on anything, that it's not just noise and seasonality? These models help you to break down this into really, really, try to break down what you see, the noise that you see into different components and try to estimate that. The way that I do it, by the way, is trying to simulate the control group. It's a really, really interesting approach, but if you want, come and talk to me about this later. I'll be happy to talk about it. And there's also a link here to a GitHub repository with a YouTube video and some code examples. So feel free to look into that. One last thing. Again, I'm not going to touch on it because of time. I just want to say one of the reasons I'm really excited about going back, I would say, to Bayesian statistics. When you use frequencies tools and when you use machine learning tools, it's a very tool-oriented approach. It's kind of, okay, what can I solve with neural networks? What can I solve with GBM? What can I solve? Okay, so you kind of start with the tool a lot of the time. Neural networks are flexible, but there is an interesting trade-off there, especially in terms of explainability. And we heard yesterday the talk about, okay, the more complex the model, then usually the less you understand different behaviors and different problems that come up from it. And if you talk about frequentist tools, okay, I have this really complicated multivariate phenomenon that's changing over time, and I want to understand causality. So I usually try to squeeze it into some model that I know, ARIMA, ARIMAX, or maybe some regression model or something else. There's usually a lot of squeezing that needs to happen and a lot of things that you need to chop off along the way just because you have a package, it kind of does what you want, but not exactly, and you need to decide, okay, maybe this package, and you try it a lot, and then you reach a dead end, and then you try another package that has a completely different setup and different trade-offs. I would say, not a very flexible set of tools. And Bayesian tools are actually, I almost want to say, too flexible. It's really easy when you work with this low-level framework to specify super, super complicated models, and then the trade-off becomes times to solve. Again, I've seen these amazing works of people doing, for example, trying to understand gas flow in pipes in order to predict problems in infrastructure. And they actually start from thermodynamic equations and build the model up from there, like these amazing scientific works, or people doing it for very practical reasons, or for in the scientific domain, people looking at equations of gravity and building a model of the distribution of galaxies. You can really go really far out. The problem then becomes time to estimate the posterior distribution. It becomes computationally heavy. But I really like the fact that kind of you have more room to maneuver, more room to think about your problems as the way that you think they are, not how the tool tells you to think about them. And I really like it. For me, it kind of brings back a little bit of the science back into data science, which is something I'm really passionate about. So again, there is a trade-off there, the complexity and everything, but at least you have the flexibility and the ability to choose how complex you want to go. And I'll, again, just mention what I mentioned before, the paper by Michael Betancourt, which is a really, really good guideline and way of thinking about complexity as well, not just about priors. in conclusion, hopefully I've convinced you that p-value is a really wonderful answer, but to the wrong question, to a completely wrong question. Bayesian models, again, can give you the answer that you need and the answer that you want to give. If you're willing to have an opinion, the prior, and you're willing to change it, both of them maybe not as hard as you, not as easy as you might think. Also, again, Bayesian tools are a really good way to start if you're willing to put in the investment to start going into this domain of having better discussions and better questions and better understanding with your stakeholders about the problem and better understanding of your stakeholders about the answers that you're giving them. So it's a really good way of opening better communication channels for you as a data scientist and for the teams that you're working in. And kind of finally, a little bit of a warning before you go out there and start, doing Bayesian statistics, especially if you're using the wrappers and the packages, just be aware of what's standing behind them. So the packages look really nice. It's almost too easy to run these hyper-complicated models. Just be aware of the assumptions behind them. If you want, I can tell you really good stories about profit versus BSTS versus other things and how, it seems things are not always as they are. So you need to be aware of what's happening also underneath the surface, not just run the command and look at the results. Be aware of the underlying models. As I said, a lot of that has to do with these underlying models of reality that you at least need to be aware of and understand before you go ahead. But with that said, I really encourage you to try these things when you go back to work tomorrow or on Monday, and think about your next test that you're going to run, or the next question you're going to ask, or the next model that you're going to build. Consider going Bayes this time. So this will be a good time for questions. Thank you.
Well, thanks for your very nice and instructive talk. As you know, in the business of, I'm also in an internet startup, typically A/B tests are not judged by one single metric, but several. And my question was, so there's a pretty well-established framework that I know to deal with multiple hypothesis testing in the frequentist domain. Is there an equivalent in the Bayesian framework that you described?
So it really depends on, the answer is pretty much yes. If you look at multiple KPIs, what you need to say is, okay, you need to have a better prior in a sense. So you need to say not just where I expect, for example, the conversion rate to live and the revenues to live after the test. I also need to say something about the correlation between them, which is maybe not as hard as you think. Not so easy, but as maybe not so hard. And again, it goes back to what I mentioned about this disciplined workflow, where you can start by saying, I can start running just without any correlation between them, see what comes out, and then make the model more complicated as we go. When you talk about the frequentist situation, you have this problem of multiple comparisons, right? Which you can abuse your model when you do Bayesian statistics, but at least multiple comparisons are not exactly a problem in that domain. So you can try different things and see how complicate the model as much as you like. But I think the answer to your question is yes. You just need to understand or come with an opinion about what's the correlation between your different KPIs. And by the way, there are tools and frameworks that will help you to do that.